So, welcome again to this new lecture of the course Solar Photovoltaics Principles, Technologies and Materials. So, first we will do a brief overview of what we have done in last couple of lectures. So, in past few lectures we looked about silicon solar cells and strategies and the design and the strategies to improve them, and then we looked at silicon manufacturing. So, silicon manufacturing is quite complex and it is very energy intensive process, and that is what accounts for most of the cost of silicon. So, although we have plenty of sand available, silicon has to be converted from silicon oxide to sand, which is a tedious process. So, first we get what we call as metallurgical grade silicon, which is then converted to semiconductor grade silicon, using Siemens process, and then we have single crystal silicon. So, this stage is all about reduction, melting, refining, and this stage is again then about this is more about deposition of silicon SiHCl3, and this converts into silicon, purer form of silicon, and then we have again solidification and melting and solidification to form so this to form a single crystal silicon. So, at this stage we have polysilicon, which is polycrystalline in nature, and then it is converted to a single crystal. So, as you can see, as you go from metallurgical grade to semiconductor to single crystal silicon, the cost keeps increasing, and this is what is the major reason why silicon is expensive. However, it is still the most common solar cell that you have in the market. So, majority of the solar cells in the market are of silicon, polysilicon as well as single crystal silicon. Polysilicon is more predominant because polysilicon is cheaper than single crystal silicon. So, as a result it is attractive for economical reasons. Now, let us look at other first generation technology, that is 3-5 solar cells. 3-5 is basically group 3 and group 5. So, basically we are talking of here gallium arsenide based solar cells. Okay. And these gallium arsenide based solar cells are based on, as we know, gallium arsenide, which is a direct band gap semiconductor of band gap 1.1 EV, 1.41 EV, not 1.1, and the band gap of gallium arsenide can be tuned by doping, and typical dopants that we use are things like aluminum and indium. So, you can have aluminum gallium arsenide ion and indium gallium arsenide and aluminum gallium arsenide. So, it is called as in gas and al gas. So, these are two commonly used forms of gallium arsenide doped with indium and aluminum, and basically for example, aluminum doping leads to increase in the band gap to closer to about 1.8 electron volt. So, and it has advantages over silicon. For example, it has higher carrier mobility than silicon, and it can be used for high temperature use, is better than silicon, and then it is more radiation resistant. So, it is good for space applications. However, it is the bad side is it is 5 to 10 times expensive. The typical dopant in in gallium arsenide are, so we use for N type doping, we use selenium, silicon, tin, which go to gallium side basically, and for P type doping we generally use zinc, magnesium, carbon, these go to arsenic sites, and the band gap, as we said, is tuned in this fashion. So, we have, let us say you have absorption coefficient alpha, centimeter inverse, and then we have, let us say, E in EV. So, if you think of, let us say this is 1.5 to 2.5, then gallium arsenide is slightly lower than 1.5. So, the band gap of gallium arsenide will increase like this, something like that, and aluminum gallium arsenide will be somewhere here. So, this is gas and this is gallium arsenide. So, this would be about 33% gallium. So, this would be 0.33 aluminum and 0.67 gallium. And this increases the band gap of gallium arsenide. So, carrier mobilities, as I said, are higher. So, mu E in gallium arsenide is about 5,000 to 10,000 centimeter square per second, and mu H is about 400 to 100 to 400 centimeter square per volt second, sorry, not second. And the lifetimes of carriers, electron lifetime is about 1 microsecond to 10 to the power 15 per Na. So, this is nanosecond. You can say a few nanoseconds actually, a few nanoseconds, and to a few nanoseconds, and tau p or tau h you can write, this is 10 to 100 nanoseconds to a few nanoseconds, small n. And so, as a result of since it is a direct band gap semiconductor, it has more radiative recombination, since it is a direct band gap semiconductor. And since it has higher band gap, the Ni is lower. As a result, Auger recombination is less. Severe. And trap assisted depends upon the quality, how you make it, and generally tau p is less than tau n for the same doping level. And dark current in these systems is generally SCR dominated, and they also have high surface recombination. So, these are some features of devices based on gallium arsenide solar cells. So, generally gallium arsenide solar cell, the design is like this. So, we have you can start with the bottom layer, let us say. So, we have N gallium arsenide as substrate, all right, and then we have the back contact. So, let us first make the device and then we will put the contact, and then another layer of, there is an intermediate layer in between, which is of N aluminum gallium arsenides of slightly higher band gap to create a back surface field which reduces the surface recombination. Okay. So, basically it is used to slow down the carriers when they move towards the electrode, because it has higher band gap. As a result, carriers will have to face a bit of energy barrier to move to the N electrode. And then we have base. So, if I make the base, this is the base layer. Base layer is made of N gallium arsenide, and this has of course 1.42 eV of band gap, and on top of this we have emitter. So, this is emitter, which is P type gallium arsenide, and then we have on top again a small layer of P type GaAs, which is again to this is called as a window. Okay. But again it reduces the surface recombination. And then we have on top a layer of zinc sulphide, and magnesium difluoride, which is ARC essentially. Okay. So, you can say it is ARC. And then we have a little bit heavily doped region of so you can say on these sides we have heavily doped region of, let us say, P plus. Okay, P plus gallium arsenide. I can write this as P plus gallium arsenide. P plus. Okay. And then we have on top the front contact. So, this is again front contact, which is generally an alloy of Ag, Mn, Ni, Au. Okay. And in this case the back contact is made up on the back side. This is a alloy of Au, AuG alloy with nickel and gold. So, you sort of you put in all these layers together so that you make a good contact. All right. So, again the work function matching has to be done so that carriers are not blocked by the electrodes, but again similar concept for the electrode. You can't cover the whole surface with the electrode because of opaque nature of metal. So, as a result you have to optimize the electrode position just like you did in silicon. These also use sometimes germanium as substrate. Germanium can also be used as a substrate because they have a good lattice match between the two, and we put N gallium arsenide as a substrate because of good lattice match, so that dislocations are smaller in number at the so defects are lower. As a result, the dark current is lower, the recombination is lower. These solar cells in efficiency, so there is a company called as Alta Devices. So, right now their solar cells show 26% for single junction, and gallium arsenide also is used in multi junction devices, and in multi junction they have gone up to about 29%. So, they have very high efficiency as compared to silicon. So, this is the typical picture of a gallium arsenide solar cell. The concepts which are used in silicon are also valid here to improve the performance. So, design considerations are fairly similar: use of ARC surface passivation, use of reducing the surface recombination, reducing bulk recombination, so on and so forth. So, these principles are valid, and so basically the device design requires one to minimize surface recombination, and for that people use these window layers, of for example you can say N type aluminum gallium arsenide for instance, and you can use back surface field layers which are P aluminum gallium arsenide to reduce the surface recombination. Often one also uses graded or differential composition in the semiconductor itself to slow down the carriers, and the series resistance is generally lowered by doping the emitter heavily, so that leads to reduction of series resistance in these materials. So these are certain considerations which are used for gallium arsenide solar cells. So in summary, what we have covered so far about single crystal so this is not the end of the lecture, but in summary about the first generation solar cell, summary of Gen 1 devices. So we have silicon solar cells, the commercial ones whose efficiency is 26% for or you can say more than 25% for single crystal silicon, single crystal or monosilicon, and about 22% for polysilicon, right, solar cells. Then we have gallium arsenide, which have certain advantages in terms of silicon because it has higher carrier mobility and so on and so forth, but gallium arsenide again is about 26% for single junction and about 29% for multi junction. But silicon is the one which has dominated the commercial market because of lower cost. So that is why we use silicon, and gallium arsenide is also very suitable for making multi junctions in comparison to silicon. Because gallium arsenide band gap tunability is better, you can use higher and lower band gaps to harness. The device thickness of this is about, let me just tell you the device thicknesses. So the base is nearly, so this is about 4 micron and this is about half a micron. So although you can have a substrate which could be thicker, the device thickness is not very large. So you don't require very large volume of material to deposit on the substrate. However, if you are using gallium arsenide as a substrate, that increases the cost, but if you can use germanium as a substrate, that will lower the cost. So absorption volume is actually only 4.5 micron as against very large thickness in case of silicon. Alright, so now we look at the Gen 2 technologies, which are basically thin film based technologies. So we move on to a new topic, which is second generation solar cells, solar PV technology. Second generation PV technologies have it mainly revolves around thin film solar cells, primarily based on inorganic materials. And the idea to use thin films is because you don't require such a large volume of material for absorbing the amount of light that you can actually absorb. So to reduce the material cost by limiting its, by reducing its amount. Okay. So, that is why thin films are going to be used, and however thin films requires to be deposited by a process which can make good quality thin films. So, that is why its development did not take place earlier, because the vacuum pumps and vacuum technology was not very mature at that time. Since in 80s onwards vacuum technology matured, that is why thin film technology also got superior, and that is why most of the thin film devices also got a kick, because of improvements in the vacuum technology and equipments. You could make cleaner materials in thin film form. In thin film form, the cleanliness is very important, because a small dust particle gets in which is of same dimension as thin film, your thin film will be dead. So, that is why you require very clean atmosphere for thin, and that is why vacuum is preferred over air. So, the type of materials in thin film technologies that we have, so inorganic semiconductors mainly, especially in second gen. I mean third gen are also thin films, but second generation are mostly based on inorganic semiconductors. So, we will talk about. So, we have first we have amorphous silicon, sometimes people also talk of microcrystalline polysilicon, where crystallite size is smaller. Then we also have cadmium telluride, which is called as CDTE, and then we have copper indium diselenide based materials and devices So, which is basically Cu indium Se2, and if you dope it with gallium, then copper indium gallium selenide, and this is mainly done to basically change the band gap. So, we will see that on the as I suggested earlier, the books you can read is you can read Thin Film Solar Cells by K.L. Chopra, and S.R. Das. Second one you can see is Handbook of Photovoltaic Luke and Hegedus, Leque. Okay. So, now thin film technologies are used, this is the genesis lies in changes, the difference in the absorption coefficients. So, if you draw for example absorption coefficients of different materials, your silicon has a band gap of 1.1 electron volt. So, let us say we plot it from 1.5 to 2.53. So, 1.5 to 2.53, this is E in EV. Okay. So, silicon has a band gap which is lower, and hence it will start at somewhere here. Okay. And this goes a little bit lower band gap, which increases somewhere around here. Okay. And then we have we have copper indium gallium selenide, which is even lower band gap, but its absorption coefficient is actually pretty good. This is Cu Se2, this is silicon. On the other hand, your gallium arsenide and CDTE both have band gaps which are about, so this will go somewhere here and it will sort of increase in the end, and then CDT has a band gap which is slightly better, like this. So, this is CDTE, this is gallium arsenide, and then amorphous silicon comes somewhere here. Amorphous, because it is amorphous, it has higher band gap, but it has higher absorption coefficient. It tends to act as a direct band gap semiconductor. So, this is amorphous silicon. So, if your absorption coefficient of material is higher, then you can reduce the volume of material that is required to absorb the same amount of radiation. So that is why the photocurrent observed from these materials is quite high. So photocurrent observed from, so photocurrent of, for example, I in case of copper indium selenide can be quite high. It could be nearly 40 milliamps per centimeter square. Its band gap is also lower and its absorption coefficient is also higher. It can give you pretty high photocurrents. If you look at in case of gallium arsenide gives you values of the order of 30 milliamps per centimeter square. Cadmium telluride gives you of the order of about 25 milliamps per centimeter square. Very high currents that you can obtain in case of cattle, and these currents are obtained at a thickness of nearly 0.1 to 1 micron, whereas in case of silicon the high current of approximately, you can reach a saturation of about 35 to 40 milliamps per centimeter square. That is obtained at a thickness of nearly 100 plus micron. So you can see that amount of material used is 100 times higher, okay, and this is a major deterrent, and this is a major motivation also to make a thin film silicon solar cell. So the idea is that you have a glass panel, all right. On the glass panel you first deposit, let us say, contact. So we first make contacts like this, all right, and between the contact we put in the semiconductor. So we put in the semiconductor, let us say, all right, and then of course you can have contact on this side also. Okay. And then on top you put a back contact, a front contact. So a front contact could be something like this. You have to isolate them though, so you make a front contact, you make a back contact, so can't make them touch each other. So hang on. So you have and then you put a top contact. So and so on and so forth. So and then of course you make a top glass cover. Okay. So you have back contact, you have front contact, and you have in between semiconductor. So for every device, if you connect them in series, then top of front and the bottom of next can be connected. So if you series connect them, that is possible. So you will have a combination like this, P, N, P, N, P, N, things like that. So that is how they will go in series. So P, N, P, N, P, N. Okay. So now these devices, the idea is here you use a glass panel. This glass panel is cheap. Okay, that is not as expensive as material is. You are putting only a micron of material, which is 100 times lower than the amount that you need to use in silicon, and then use a front metal contact, which can be put by process like evaporation or something like that. So the advantage here is that you are able to make a junction, and this is from the front the light will come. Light will also come from here. So, you can also illuminate from this side, because on one side you have glass, on the other side it is open, or you can put something else on top as well. You can put glass also again on top. So, light can come from both the sides. This also gives you a freedom in terms of choosing the electrodes. So, use very thin amount of material, you can throw the light from any side. That is why there are two configurations which are possible in thin film solar cells, substrate and superstrate. The light can come from either side, and it allows you to reduce the amount of material. So, this is the motivation behind using thin film solar cells. This was the motivation in second generation solar. So, we will stop here today. We will now discuss the thin film technologies in terms of materials and issues in the next few lectures. Thank you.